talks. All speakers here. Shobhit Bhattacharya there. And Sumant Chandari. So then Karan is here. Okay, maybe he'll be in back. Okay, so first talk is by Parthasarathi Majumdar, Black Hole Entropic View on Neutron Star Mass.
Thank you very much, Ramesh. It's wonderful to be here. Of course, I come here every now and then, but it's wonderful to be among so many old friends and many new friends as well, some students and postdocs and so on, with whom I've worked, and I'm really enjoying this meeting. Thankful to Amitabh for providing all of us the opportunity to share our views. Now, as soon as this title appeared, a neutron star theorist, Professor Jishude, commented that, how come you're encroaching onto our domain? So I would like to say that I have no desire to do that, except I think the problem is still very hard. So what is the problem? And of course, you know, like so many of us do, we always try to... that's something which I didn't say anything more offensive, right?
Really wrong.
I haven't said anything yet. Right, so some neutron star facts. This is known. I got this number from my friend who's also a neutron star theorist. This seems to be the best bet so far, rather accurate measurement of the largest neutron star mass observed so far. And this is weird. I mean, how come you don't have neutron stars which are heavier?
So there is perhaps one, 2.7.
Sorry?
There is one, 2.7.
Well, this is the number he gave me, 2.7. He said had some other corrections and so on.
Yeah.
But it's in the same ballpark as far as I'm concerned. It's not the precise number 2. But the funny thing is that you have black hole candidates which go from 5 to 5 billion solar masses. So there's clearly a very deep distinction between these two categories of things, astrophysical objects.
Black hole is profound.
If you would get murdered, I'm not going to
Soon to be compared with the ordinary thing.
So this seems to be that perhaps this object is not so stable under gravitational collapse, that if the mass exceeds 2.5 or 2.7 or something, then this thing just collapses and becomes a black hole, which is why we don't see neutron stars. Neutron stars, I mean, most of you will know that all pulsars are neutron stars. Of course, not all neutron stars are pulsars, but you know, there is good data on these things, much better than on black holes, precision data. But there's another aspect of it, which is also very weird, which is the size to the Schwarzschild radius ratio. The measurement of size is difficult, I'm told, but you know, even if this is correct, this is so close to the Schwarzschild radius. Okay? So this is the Schwarzschild radius, and this is the neutron star size. Now if you compare this with white dwarfs, 10 to the minus 3, Sun, 10 to the minus 5, Earth, 10 to the minus 8. So you begin to wonder what is keeping this system from collapsing. I mean, it could be both ways. There was something really mysterious going on. What is the standard view? Well, it's hydrostatic equilibrium adapted from Chandrasekhar's work on white dwarfs. So basically, it's trying to equate the gravitational pressure to the Fermi pressure. And the gravitational pressure for spherical GR stars is obtained from this famous TOV equation, which gives you the core pressure with some approximations. On the other hand, the Fermi degeneracy pressure, actually, in the case of neutron stars, is a very difficult object to compute because it strongly depends, it depends on strongly interacting quantum field theory and the neutron star equation of state. And we have Professors Days here, who spent a lifetime trying to change such equations of state. There's a so-called model-independent approach, Rhodes and Ruffini, dates back to the 74, but they also have a kind of fiducial use of a particular equation of state, the Harrison-Wheeler equation of state. The bottom line is that, I mean, this is something which I found in Chandrasekhar's Nobel lecture. This is something very weird because nobody reads Nobel lectures. It's not there in any of his other books or so on. Excuse me. And he...
Question.
Yes.
So, for non-relativistic matters, so usually P is 0, much less compared to
Yes.
rho.
Yes.
And for radiation, this the constant is 1/3.
Yes.
So usually one expects that the state parameter should lie between 0 and 1/3. So
Well,
relative-
yeah, that is perhaps true, but it could be, it may not be a power law at all. There will be predictions because it's a strongly independent system. Okay? So we imagine that P is some power of rho. That itself is a simplification. That need not be there at all.
Like for electron degeneracy pressure.
That is the problem.
For
But,
electron degeneracy pressure, the pressure goes as rho to the power 4.
yeah, but I'm coming to that actually in a second. But the
Polyton.
point that I want to bring to your attention is this. I mean, this is something I just took off from Chandrasekhar's Nobel lecture, and I found this constant. Now, this is
Just
something
one
which...
comment.
Yes,
Although you have written model-independent approach.
yeah. This is not quite model.
No, that's what I'm saying. Here, what is done is that for the envelope, you have some standard equation of state.
That's right. That's right.
Inside,
You interpolate.
You interpolate.
Exactly.
So it's not model.
It is not, so that's why I put, inverted commas, because they claim, there's a PRL paper in 1974, they claim it's probably,
But it's a good paper.
it's a good paper. It's very good. But this sort of, struck a bell with me because of my interest in quantum gravity. And I felt that perhaps this was worth a look. So I wasn't going to encroach into your territory. That was not the issue. But I just felt that, could it be? I mean, this is this possibility which lurked in my mind, for which I found this fascinating. Could it be that in some way, quantum gravity is appearing in such an object as a neutron star? So this is, could it be that this is somehow a little bit of an indication that quantum gravity may be relevant for physics? Okay? I mean, observation. So that was sort of my motivation. I was really inspired by this. And I gave a preliminary version of my thoughts in the Chandrayaan Centenary celebration. So, what was it? But there is something that I have to say, I felt that was important to mention about the hydrostatic equilibrium. You see, when you calculate the core pressure, it's in curved space-time. But the degeneracy pressure, like I think somebody just mentioned electron degeneracy pressure. If you look at Chandrasekhar's derivation or any derivation, it's a huge number of textbooks. It's in flat space-time. In fact, not even in special relativistic space-time. So you wonder if there's an inconsistency. I mean, I remember, consistency being a sort of a huge requirement of all of us. And how come this great man was able to get away with it? So I just felt that could be fortuitous. And then I realized, no, this is actually something else. I mean, there are examples. Mitchell's derivation of the Schwarzschild radius, he gets the factor of 2 right, and there was no GR at the time. Bohr's derivation of the Bohr radius of the hydrogen atom precedes quantum mechanics. Bette's explanation of the Lamb shift using non-relativistic quantum mechanics, when you know that the thing has to involve quantum field theory. So I think there are examples like this. I think these guys are great guys. They really understand the physics, but they don't have the math. So they somehow are able to pinpoint the physics that's going on using the apparatus, which is not so good. I mean, this requires insight. Okay? And they expect that future generations will steal up, will pretty up the mathematical apparatus.
I think the more thing is, in all these cases, presumably the situation is so symmetric.
Well,
So that takes that thing.
But it's not just
I
that.
don't think that this your
It's
Mitchell's
possible what you're saying.
Laplace derivation. No, they didn't understand any physics about it. But the situation was just right.
wrong.
Because they totally,
Yeah.
because the
Yeah, I agree.
conceptually
Yeah, I
they are
agree.
totally wrong. There's
Yes.
nothing
no, absolutely. I mean, they didn't have the theory at all, right? So I think that's true for all.
Bohr is
But I just felt that,
No,
I shouldn't.
I don't say that it is not
I want to dismiss them because I think what they do is because the agreement is so good, right, in all these cases, they sort of push you towards the right theory, which will then agree with the experiment even better and provide corrections. So that's it. Now, what is the problem with the standard approach? Again, this is not a problem so much as a difficulty. The equation of state is poorly known for core densities which are of that order, 10 to the 14 grams per cc. And standard practice, Professor Jishnudev was talking just about these things, the inclusion of hyper-on resonances, quark resonances. So you are talking about quantum field theory. Now, this is quantum field theory in the strongly interacting regime, okay, which is very difficult to work with, as we all know. I mean, you know, the old pion-nucleon scattering theory failed miserably when he tried to do it perturbatively because the coupling constant turned out to be 15 from experiment. So this is a theory which is not quite a theory. It's an approximation to some theory, and we know what that theory is. It's QCD. And you know, they use things like the bag model, which are already antiquated from the QCD point of view, okay, to extract parameters that they use in this theory. So
We use the large.
no, I'm not talking about you, but I'm talking about, I mean, this is sort of, I'm talking about, you know, things more generically. And the most important feature as far as this is concerned is that it still uses special relativistic quantum field theory, which is field theory in flat space. But as you know, if you're inside a neutron star or anywhere close to the center, you are not in flat space-time at all. So he said, okay, no problem, I should do curved space-time field theory. Well, that would be the standard approach, but curved space-time field theory, as we have some experts on that too, and that's a horrendously difficult subject because of technical complications like this. You don't even know if, you know, without additional assumptions, even something like the spin statistics theory cannot be taken for granted. So it's not an easy job. Most of the work that goes on in curved space-time field theory focuses around simpler objects, simple predictions, where all these additional assumptions will be valid. But in general, we have these huge problems. So my point was, can we get around it? Can we have a different take? So this is,
There's
yes,
one
please.
comment I would like to
Yes,
make.
please.
You see, that density is just a few times the nuclear density. So you mean to suggest whatever you are going to say should be almost applicable to nucleon and the nucleus.
Yeah.
So you will have to somehow leave very dangerously.
Yes.
I mean,
That's the thing. That's the thing. I mean, you're right, absolutely. This is, I think neutron star physicists do live dangerously. Sure, they would agree. But on the other hand, you have good codes and some of them work, and there's agreement with experiments. So I'm not going to throw all of that away. I'm simply going to suggest, even if all the codes work out, is there another way of understanding what we do? Is there another way of, I mean, what I'm saying could well be a fairy tale. This is not as rigorous as some of the talk that went before. But on the other hand, it may not be, and I'm going to try to persuade you that it isn't a fairy tale. So the fairy tale begins with this noticing that this maximum mass, which people have written down from various considerations, can be rewritten in that form, where ACN is simply the quantum wavelength square for the neutron divided by Planck area. And what struck me most was that this is a ratio of areas. It's a ratio of areas where this is the Planck area. And I kept wondering, would this then mean that quantum gravity will be away? And of course, if you think about it like this, you see, Partho mentioned it, when you set the Planck scale to 0, this one does not go to 0. So even if there is some aspect of quantum gravity which comes in here, it cannot be perturbative, because perturbative quantum gravity affects a power law.
Just apart from here, you would have expected it to go with volume.
No, that's the whole thing. This is something which people have written down. I'm simply taking their formula. It doesn't go with
No, no,
volume.
so that's why I'm more confused. My question, this is for the black hole, the horizon you can understand.
Yeah, I mean, don't steal my thunder. Hold on, half an hour. I'll be done with it at the time.
This AP is Planck's area.
Planck area, 10 to the minus 66 APs.
What is CN?
ACN is simply lambda Cn squared, that's the Compton wavelength. Because black hole entropy has a leading term which is proportional to the area of the horizon, Planck area. So, and we know that black hole entropy, from what Park had said, and generally we know that black hole entropy, the very existence of black hole entropy, has to do with quantum gravity. Without quantum gravity, there is no black hole entropy. Classical black holes simply do not have any entropy. So that is where I started pushing this idea, and that is perhaps justification why you see the word black hole entropy in the title of my talk. So let me try to motivate this a little bit more. So the maximum mass for stability of the neutron star, with some hand waving, can be thought to be the minimum mass for the formation of a black hole horizon. Because if you exceed it, I mean, that's the supposition that if you exceed the maximum mass, then there's gravitational collapse to a black hole. And this I already mentioned, so this is a speculation. So could there be a possible entropic origin of critical mass which does not depend too strongly on the neutron star equation state? Okay. And also, this other speculation, the formation of the horizon. Now, usually, the way we think about the formation of a horizon has to do with some kind of a critical density. If the critical density, we put enough matter within the Schwarzschild radius, then, I mean, if the length scale associated with the matter is of the order of the Schwarzschild radius for the given mass, then you expect collapse to happen. So in other words, if you try and make something very heavy, keeping the volume the same, then you expect things suddenly to collapse. But I'm just proposing something different. I'm saying that the horizon formation will not be all of a sudden. It may be like a first order phase transition through a nucleation process. Which means that what I'm proposing is that there is a small nucleus which forms, and then whether the nucleus grows or decays decides whether at the end of the whole process you have a black hole or a stable star. That's the kind of picture. And I'll show you a picture also of what I have. So this is going to be a fun talk from that point of view. And I assume that, these horizons, of course, will be evolving horizons, otherwise called trapping or dynamical horizons. And they evolve, so the time scale is such that there's a trapping horizon which evolves to an isolated horizon, which is like an equilibrium configuration, and then it starts evolving again and becomes isolated and so on. So you have quasi-equilibrium configuration in the evolution. That's an assumption. And this assumption is necessary because that's what I know how to do. Okay, so it's kind of tailoring the problem to something I can handle. That's the reason I'm making this assumption. Okay, so this is again something which all of you know, what sort of a boundary are we talking about. So we are talking about an inner boundary of space-time, and that is not an event horizon. Again, these are things which are known. There are problems with thinking of the event horizon as a boundary. So instead, we have a trapping horizon, which is a non-stationary, marginally after-trapped hypersurface. We assume that for simplicity, that is topology is our process too, and you can associate a mass with it, which is not possible to do for the case of the event horizon, because the event horizon has to be globally stationary, and there's a global description. This is a completely local description. So that you can associate a mass which is related to the ADM mass, and this is whatever is in between, energy of whatever is in between. So that's kind of relation. So you can define a horizon mass like this, and this is what comes from the non-stationary aspect of space-time. And like I said, it equilibrates thermally to an isolated horizon, which is a null inner boundary. So this trapping horizons are not, they are boundary of space-time, but definitely not null. They are space-like or time-like, depending on whether they are accreting or emitting. And the equilibrium configuration, again, because of simplicity I described this, is a boundary of constant area, yet local and non-stationary, which means that we assume that there could be stuff around it, but nothing is crossing it. That's basically what isolated horizon.
If it is non-stationary, can it be thermal equilibrium?
Well, yes, it can be, certainly. It can be, unless the area changes. So that's the thing. The area isn't changing. So this is not a radiant horizon or an absorbing horizon. That is trapping horizon. So I'm thinking of a situation where you have a trapping horizon which equilibrates temporarily because the time scales are such. because I can then work with this object. And that's the most important.
So basically you want something adiabatic kind of.
That's the thing. It's an adiabatic process. Good. That's nice. Thank you. So I have a picture now. This is I like this thing. Again, this talk is mostly about this pictures and so on, but I have some maths later. So this is a collapse, which you can probably see very easily. A neutron star collapsing to a black hole, a standard description. But there's another one. Then, and if you look at this one in contrast, so the black hole grows inside, so the horizon grows inside, but then it decays. And that's how the neutron star stabilizes. So the stability or otherwise of the neutron star has to do with what the horizon does inside. If the horizon keeps growing, it will engulf the neutron star, and that's when we say a black hole is born. So there's a horizon which is growing, eats up the star, and then you begin to see the horizon. So nobody sees the horizon, but that's when we say that the horizon is formed. Okay? On the other hand, if this happens, then whatever internally happened, the horizon simply decayed off, and you're left with a stable neutron star. There's nothing eating the neutron star.
This horizon is a trapping horizon, not
It's a
the
trapping
event
horizon. It's a trapping horizon.
Is this formation meant to leave it in the same state as before?
I'm sorry?
Is this meant to leave the neutron star in the same state as before the trapping
Yeah,
horizon?
this would mean that the neutron star would stabilize if this were to happen. Okay? And if the other thing happened, the neutron star decays.
So you expect the neutron star to bounce back instead of
No, well,
collapse?
probably doesn't bounce back, because you see, the thing is that if you look at how a neutron star is born, it's born after a supernova explosion, and what you have is something called a proto-neutron star, which is hot. And then it cools down, shrinks. Now when it's shrinking, either it continues to shrink all the way to a black hole, or it stops. So these are the two pictures that I'm trying to show. Again, this is fairy tale, this is just to aid our thinking.
But Partha, you are getting in the two pictures. In both pictures, you say that at the core of the horizon, the trapped horizon forms, right? Now, in one picture, is the trapped horizon decays.
This one.
Then it leaves behind the neutron star. Other case fellow is the trapped horizon eats up the rest of the
Right.
becomes a black hole.
That's right.
Now, can you tell me in the two things?
What is the condition for each to happen?
What is the physics? You see, it is I thought that everywhere the phenomena is of collapse.
Yes, I mean,
So I don't understand. So
there is-
on the other hand, basically the question is, what is the condition in which the horizon operates?
the condition. I'm going to give you a condition. That's the whole thing. I'm going to derive a condition for you. Whether right or wrong, that's a separate issue, but that's exactly right. Under what condition? So I'm going to try and formulate the problem precisely. I'm running out of time. So I will fall short of time, so I should skip several. First of all, get out of this. Well, let me skip this because this is just the Penrose diagram version of what I said. Let's just skip this. So this is basically the thing that I'm into. So we talk about quantum general relativity without really talking about a particular version of QGR or quantum gravity. But in any theory of relativity, you have a state which is an element of this sort of Hilbert space, where HB is the bulk Hilbert space, HH is the Hilbert space which I shall associate with the trapping horizon, and this is the Hilbert space associated with bulk matter. Okay? And of course, this need not be diagonal, there could be entanglement, and the Hamiltonian acting on this Hilbert space will therefore decompose like this, and therefore we will have a bulk Hamiltonian constraint, which involves both the bulk Hamiltonian for gravity as well as the bulk Hamiltonian for matter.
We talked about this a few years ago, I think.
This, like I said, this was Chandra's.
But I also objected then. Nth states never formed by Hamiltonian layers.
Nth states.
We know that such things happen in topological insulators and so on.
Well,
But it's never like this.
so you're saying that this decomposition is not right?
You don't have a Hilbert space at the edge, Hilbert space at the bulk, and it's a tensor product. It is not like that.
in practical, experimentally verified?
I think the supposition here is that there could be fluctuations of the degrees of freedom on the horizon.
How do you describe those?
Yeah,
Quantum
can
field
I?
theory.
Yeah, I'd like to
The
come
quantum
to
field
those.
theory.
I'll come to those.
Because fields you cannot restrict to an edge.
But this is okay. So this is really for situations with gravity. And if you didn't have the matter, then we already know the description of black holes where this is implied.
That is not classical.
No, even at the quantum.
There is no way you can restrict a quantum field to a surface. Barclay's theorem.
Well, no. I think that's not the idea. The idea is that there's a whole description of which you can associate. So let me go on. I mean, I'm running out of time, so maybe I can postpone the answer to your question later. Okay, so since I'm really running out of time, what I wanted to show is the following. So if you wrote down the partition function, okay, in a canonical formulation, then what you will get is because of the annihilation of the bulk states by the bulk Hamiltonian, this partition function turns out to be a partition function that lives only on the boundary. And this is to say that the bulk states will decouple from all thermodynamic formulations, and this is what I call thermal holography. This is sort of a weaker version than the holographic hypothesis, but this I claim is sort of a plausibility argument, whereas for this is not related to some sort of a plausibility argument like this, but it's a very strong hypothesis. Lots of work that has happened on this. Now, I now appeal to any kind of quantum gravity where we have quantization of area, similar to what Dr. Mitra was talking about. I also assume that in this description, the area of the neutron star, ANS, is also quantized in terms of Planck area. That's sort of tautology at some level, because you can always say the Planck area, the neutron star area is a huge number times the Planck area. This is a large number area. And I make things dimensionless. There is another scale involved, which I shall come to later on if I have the time. Let me just go on with this. So the assumption here is that on every spatial slice, there's quasi-equilibrium with a fixed area of isolated horizon. Spatial slice quasi-equilibrium means that we have an isolated horizon in fixed area, and the mass is a function of that area. And likewise, the matter around that isolated horizon is a function of an equilibrium, neutron star area. Now, if you follow what we had done earlier for black holes, we will try to compute this boundary partition function around this equilibrium configuration in the Gaussian approximation, then what you get is this. And this formula itself gives us a condition like the condition you're asking about, and that's called a thermal stability criteria. So what happens is if you have an extremal point at this point, at this pair of areas, horizon area as well as neutron star area, then the Hawking temperature turns out to be like this. And also, there's a saddle point condition on the Hessian. Just by requiring that the integral is meaningful, you get this kind of an inequality. Okay. So S here is simply the microcanonical entropy for the degrees of freedom associated with matter, for the degrees of freedom associated with gravity. This is the mass associated with the horizon, this is the mass associated with the matter, and that's the inequality. If this criterion is satisfied, this is the criterion for stability of the horizon. So the stability of the horizon guarantees, stability and then growth of the horizon guarantees that you have collapse. If this condition is violated, then the neutron star stabilizes. Okay? So we have a quote-unquote precise way in which we can formulate this condition. And of course, what we haven't done is to show that this leads to a maximum mass for a stable neutron star. We hope that this set of equations, you can see that these are differential inequalities which are not easy to handle, but I'll continue with that. So, but before that, let me make a little digression for about 2-3 minutes to say what is the situation for black holes. So if you have black holes which are radiating, you just forget about the existence of matter outside a black hole. Okay, so you set some terms to 0, and then you have this as a criterion, thermal stability criterion for a radiant black hole. In other words, we have not ever used any kind of metric. No classical description was involved in this at all. And yet we are trying to predict whether if you have a given mass and a known function, mass expressed as a function of the area, then this condition, if it is satisfied, should lead to a black hole, which is stable. If it is not satisfied, then you have a thermal instability. So, again, if you just write this down, in open terms, open it up, then this is what it looks like. And I was amazed. I happened to visit Wald at some point and told me about this kind of criterion, which they have discovered purely classically. And we tried very hard to match this one with this one. Ours does not ever use the classical metric. Wald's does not ever use any kind of statistical mechanics or anything of that sort. But they seem to be very, very similar. So I'm quite intrigued by it. I don't know why they should be similar. And it generalizes to charged horizons. And more recently, a student of mine, his name is Alok Sinha, has generalized it to rotating charged horizons and in arbitrary dimension and so on. So there is no classical metric used in this derivation. And what is important here is, of course, that there are corrections to the area. Because you see that if there are no corrections, then this one does not have any sense. You must be able to take a second derivative, and that must mean something else. Because otherwise, this is zero. And all you get is the fact that the mass is a positive quantity, which is not very meaningful.
So, I missed something. So, how do I read this independently?
Okay, so these AHs are simply derivatives. So MH is a function of AH. This is the second order derivative divided by, it's a logarithmic first order derivative, and likewise for entropy, right? So if you have this as the entropy, then you are guaranteed that this will lead to some meaningful result. Or any other, in another theory of gravity, if you had corrections such that this wasn't zero, then you automatically get a strong bound. So there are some fiducial checks. So although we didn't use any classical metrics, suppose you now went back and said, hey, wait, I have classical metrics and I know how to compute the mass as a function of the horizon area. For instance, this is the formula for Risonov-Strom. And then you know for sure that this will violate the stability bound. So this is the Risonov-Strom in asymptotically flat space-time. And that, of course, has this instability under Hawking radiation, it just decays away, right, as we know. On the other hand, if you had ADS Risonov-Strom, then that is not the case because this term dominates and that leads to a stability bound so long as the area is much larger than the cosmological constant, the inverse cosmological constant. So there are situations where we have bounds, in one case leading to stability and the other case where it's not. But these I call as predictions, you see, because we did not use anywhere in the derivation any classical metric. Okay, so therefore the derivation somehow seems to agree with these fiducial checks. But now you give me any black hole in any dimension expressed as a function, where the mass is expressed as a function of the area, and I could tell you whether this thing would be stable under Hawking radiation. That's the claim. Okay, now I think I should not spend so much time about isolated horizons and so on because I'm supposed to finish at 3:15, right? So I have 10 more minutes or something?
10 minutes.
10 minutes, okay. So, well, this is just to say what are the characteristics of the isolated horizon. Like I said, it's a null inner boundary of space-time. It's marginally cracked outer surface. The area of the horizon, of the spatial slice of the horizon is a constant. There's a zero law one can associate it with it. So there is there is something called a surface gravity. But unlike for the event horizon, where you have stationarity, global stationarity, this is not the case here. You can define mass on the isolated horizon, and mass is related to the area mass by this sort of formula. And this leads to a first law. So one can derive a first law of isolated horizon mechanics, just like the first law of black hole mechanics. The isolated horizon, there is no second law, however, because you see, I cannot, by definition, have an isolated horizon whose area is changing. And unless I have that, I cannot actually talk about a second law. So the moment I change, I allow the isolated horizon area to change, I'm in the domain of trapped horizons. So that's another matter. And for trapped horizons, there is indeed a second law. Okay? But this is something which we know and how to deal with, so that's nice. So I'll tell you maybe in 2-3 minutes on how to deal with this very, very quickly. First of all, again, something has been said already, but because it's a null boundary, there's the metricon, the induced metricon is degenerate, and therefore the only kind of theory you can have on it are topological gauge theories. Now, if you use the connection tetrad formalism for describing gravity, then this is the SU2 bulk space-time connection, and the pullback on it is this connection here, SU2 connection on the isolated horizon, gauge connection. And therefore, the kind of theory one expects is an SU2 theory, which is completely topological. And there are not that many candidates. It turns out there's actually only one candidate, and that candidate is given by this set of equation, this equation. This is the Chern-Simons equation. The sigma I here is what is called a Solder form. It's basically some sort of exterior product of tensitized triads on the isolated horizon. So basically E wedge E, where E is the triad on the isolated horizon. And K is the same K which Parker has written down. I forget the number of pi's I had, but he had, but this is basically the same thing. AP is the Planck area, gamma is the boundary of density parameter. So this is a Chern-Simons equation. And this is, again, you can derive it in one of very, very many different ways. So given an isolated horizon, you have a Chern-Simons theory on the boundary. Okay? And the idea is that we can quantize this theory. So this is the Chern-Simons action, and that's what I mentioned. So then, the way one has to think about this is that there are Chern-Simons degrees of freedom on the isolated horizon, which are coupled to the bulk sort of forms like this. So you can think of this equation as field strength or curvature of the degrees of freedom associated with the isolated horizon, driven by this source. The source is bulk gravity. It's right here. Again, I have to skip this stuff and just come to the pictures because I don't have time.
Isolated horizon itself is a boundary.
Yeah, that's what I said. That's what I said. Okay, so this is
On
what.
that boundary, you have another boundary.
No. Well, that's just slice. It's an intersection. When you take a spatial slice, this will intersect at two spheres. It's not a boundary. If you have a boundary, you can't possibly have a boundary. Right. So this is a picture. Right?
Neutron star?
No. This is simply a picture of what quantum space would look like. Okay, from this description. I did have some details, but I don't have the time. So I have to run through this because I want to tell you eventually come back to neutron stars, right? So this is a spin network. Now I know that Miladi was sitting next to me and she was asking about this. Martha didn't quite explain what were the punctures and so on. So basically this is a picture of quantum space. Quantum space is now a network. And this is something that you can derive. This is not a fairy tale. This thing describes a network where the edges, given as colored lines here, carry a spin. So the color coding is that of spin. Spin being the SU2 quantum number, the SU2 representation number. Spin half, 1, 3 halves, etc. And you can see that it's oriented and closed network. It has to be closed because the closure, you see, it's graphs like this which will eventually be used to construct the quantum states, bulk quantum states of the system, and the quantum states must follow SU2 invariance, so they must be subject to annihilation by the Gauss law constraint as a quantum constraint, and that requires that all the lines should somehow close up, and you have oriented lines because there is spin, and these gaps here in space are of Planck scale, which is why you don't see them. Okay? Like you don't see the holes in my kurta. If you did, I would be wearing this. So, again, the neutron star. Well, actually, this is not quite a neutron star. This is really a black hole. But this is where the punctures come from. So I have that space, bulk space, and I put the sphere. So
This is
sort
after
of-
time slice.
It's a time slice.
After time
Yes,
slice.
sure. I mean, when you do canonical quantization, usually you do things on a spatial slice. And that's part of the problem of canonical quantization, that you choose a time. Okay? So it's in that sense, I mean, this is after all a non-perturbative, background independent canonical quantization. Now here, bulk spin's edges then puncture. So this is what we are going to talk about horizon, but the horizon is now going to be constructed out of these punctures. Okay? So we don't have an independent horizon being punctured, but basically it's a set of punctures which construct the horizon, and at each puncture you have a deficit angle, which is a function of the spin carried by the line which is creating the puncture. Okay? So again, this is what it becomes. You see, again I have to really rush. Oh my God, how much time do I have, Ramesh? 10 minutes?
5 minutes.
5 minutes. Okay. This is a problem. So anyway, this is the quantum equation of a quantum version of the equation I wrote down. The delta function here tells us that this is point-like things. So, oops. So the only kind of degrees of freedom are these, which solve this equation, are these connection fields. The connection fields are like this. They are pure gauge everywhere except at the punctures because of the nature of the source. However, you can go to what is called the weak field limit. And if you go to the weak field limit, then the situation becomes very simple because those then only need to go around one of these punctures, so they decouple in some sense. That's the decoupling. And the weak coupling limit is exactly the limit that Parthasarathi was talking about. It's a large scale limit, k going to infinity limit. And in that limit, you see, what happens is you can then argue there are no charges inside, so by Gauss's law you can just turn it around. No Chern-Simons charges inside the volume, and therefore the Chern-Simons Hilbert space, the Hilbert space associated with this sphere, is simply the SU2 invariant part of the Hilbert space associated with each of these punctures. Okay, so only SU2 singlet states will contribute, and that happens only in the weak coupling, the large K limit. Okay, so again I shall skip this part and come to the entropy. So here you see some of the things which you saw in one of the earlier talks. So what we are computing is the dimension of the Hilbert space of the Chern-Simons theory, and that, according to this beautiful paper of Witten, is given by the number of conformal blocks of the SU2K West-Rubin-Witten model, which lives on this punctured two-sphere. So we had the whole thing, S2 cross R, that's what the Chern-Simons lived on. But Witten is telling us that the dimensionality of the Hilbert space there is simply the number of conformal blocks of the West-Rubin-Witten model, and you can compute it using this machinery of conformal field theory in 2 dimensions, and this is the formula you get. So anyway, let's get on with this. I mean, I just wanted to mention that there is an interpretation of this which is exactly like the entangled entropy interpretation. So you have bulk states which can be thought of as pure states, and then when you trace over the bulk, trace over the V's for volume or bulk states, what you get is a reduced density matrix, rho B, which involves the boundary, and this 1 by 1 formula then gives you the entropy computed from the boundary, and this exactly gives us the same result which I showed before, and there's a correction to the Hawking temperature as well. And anyway, so what is the implication? Coming back to neutron stars, we are going to use this idea of stability of a horizon, coupled with the fact that this horizon has corrections beyond the area of, to discuss the stability. So define the neutron star mass on each spatial slice, like so, and then stability depends like this. So I'm just going to, again, because I'm running out of time, give you the 2 conditions which you have to look for. Determine the maximum neutron star mass at t equal to 0, for which the area of the horizon shrinks to 0. If it does, the neutron star stabilizes. Alternatively, determine the minimum neutron star mass for which the area and the neutron star, so the neutron star becomes nothing but the neutron star simply becomes identical with the horizon area. So the horizon goes and peaks and peaks. Beyond, of course, t equal to infinity is not quite right. That happens in a finite time, so this is incorrect. So that happens in a finite amount of time. But this really means some large time, so you wait for a large time, and if you find that the area of the horizon inside vanishes, then that means that the neutron star is stabilized. If you find that the area is equal to the area after some large time of the neutron star is just about to be eaten up by the horizon. That's the formation of the horizon, and it is collapse. Okay? So again, this is, so the question is how much of this can be done. I think I have to stop now, but I have tried to bring in the idea that S matter is also a function of lambda 2CD in a sense, or AN, and that leads to certain simplifications. But this is really work in progress, so I can't say much more than this. So let me just make some statements. It's a fascinating interplay between low energy strong interactions, very difficult field, and strong gravity. My proposal now is to calculate the matter part of the entropy, which figures in these calculations, from something called holographic entanglement entropy. Now, this is something that comes from the string theory view. So this is again an effort to try to join the two fields together. The gravity part of the entropy is calculated from the loop quantum gravity description, but the matter part is very difficult to calculate from the loop quantum gravity description. On the other hand, these people have been working on this for a long time. So is it possible to do it? And their results are extremely encouraging. This is the kind of results they have for large areas compared to some sort of ultraviolet cutoff. There's also a built-in infrared cutoff in this problem because the neutron star has a finite radius. So I think there is some hope in this, and that's really what I have to do. Now, of course, there are many issues here. Maximum mass for, I'm done. So I have assumed that the maximum mass for neutron star is close to the minimum mass of collapse, which excludes the contribution of gravitational waves. Now, gravitational waves are, of course, there. There's no question about it now. And therefore, one might have to take this into account. In the conventional way of looking at it, if you have a stiffer equation of state, that leads to higher maximum mass. A softer equation of state, lower mass of hadrons and quarks. So a stiffer means that the constituents are much higher mass, so you have higher excitations in the hadron spectrum. If you don't have that, it's a softer equation of state. So you have to postulate low energy strong coupling theory of hadrons and quarks. So this is really hard. Okay? Here, what we're postulating is the existence of a partially trapping horizon, and the stability or growth of this horizon as an alternative criterion for which eventually should enable us to calculate the neutron star mass. This is a critique, which of course would be obvious, but then you see the way I'm thinking about it is how does this horizon form? So there I'm influenced by statistical mechanical thinking that in any first order phase transition, the first formation of the nucleation bubble is always like a fluctuation, a statistical fluctuation. So even though mean densities are not large enough perhaps, or maybe they're close enough, but not really large enough perhaps, there could be density fluctuations. Okay? Because remember, this is a a proto-neutron star is a hot, dense system, which may go either way. So I think this is really a very, very critical phenomena kind of thing. I mean, it's so fascinating that even though I have not made any progress, I really can't get away from it. It seems to me that there must be a beautiful answer to this. And this beautiful answer somehow tells me that it cannot depend too strongly on the precise equation of state and what I put in my equation of state. That's really the key point. And to my great surprise, I found that some neutron star theorists who have done a lot of simulations have come to the similar conclusion that somehow the critical mass may not be too sensitive to the precise equation of state. I don't know if you'll agree, but this is something I've heard. There's somebody called Eunice, who has something like this to say. Vicar Hussain told me about it. The stability criterion, well, okay, it matches the black hole limit rather nicely, and it permits a precise formulation. So I need to explain further. Thank you.
I have some. So first of all, I don't know why you have to go to neutron star. All you could have said is a ball of gas trying to collapse. Because in order to go to neutron star, we already know some of the mechanisms that take place when the supernova explosion takes place. For example, slightly heavier, you have the implosion explosion cycle, which actually will violate some of the things that you have in mind, unless the time scales are properly fitted in. I don't know whether you have looked into it.
No, I
Then
haven't.
the neutrino that carries
Neutrino
out.
emission is something I haven't thought about, but I don't have anything
No,
to
but
say.
these are the points which might actually
Influence.
destroy this nice effect. So if you consider the ideal ball of gas collapsing, what
So
you are
it is
making-
actually that at this point.
Okay,
It's not
that
very
is what
different
I'm
from
saying.
that. But I always think of finding a context to discuss a particular problem. And this would be the context. I mean, otherwise, why would I even bother about it?
And lastly, about your dependence on the equation of state, it's possible, quite possible and logical to think also that it will not depend exactly on this.
Not too sensitive.
Too sensitive.
See, there is already a dependence,
Yeah.
because this will come through the cutoffs in the matter theory, matter quantum field theory. So there will be some dependence. But do I need to know the full quantum theory in detail?
But
Because it's a strongly
But
dependent.
the theory that we are doing is no less easier than doing QCD. Rather, since the gauge parameter is becoming weaker and weaker, I would say that one should think using comments from QCD as well. Some
Yeah, see, the only thing is that then you have to do QCD in a curve pattern. That is very hard.
that will not really matter very much, because if you think of the curvature, that is, here you see when you have the self-bound system, like say strange star, okay, the gravitational contribution will be of the order of say 15 or 20% only. So
Okay.
even less.
Maybe this is something.
Let's get others also in, yeah.
Yeah, so one thing is that where is the fermionic nature of the neutron coming in? You see, if neutrons were not fermions, they would have collapsed in any case. It is the degeneracy pressure which keeps it against the gravitational collapse till a particular point. In your approach, it appears that the fermionic nature is not important. Rather, you are getting a criteria of the maximum mass purely from quantum gravity. So I'm a bit puzzled about it because
Well, part of it is simply the fact that, if I have curved space-time, what's a fermion? I mean, that itself gets to be very, very tenuous. Right? To define a fermion, I don't have a spin statistics theorem in general. May not be.
That statement is not correct.
No, it's there only for globally hyperbolic
Your
space-times.
backgrounds, there are,
For globally hyperbolic space-times, there are. But if you have ADS, that's not globally hyperbolic. So.
I mean, there are now space statistics theorem using compact space-time regions where people have quantized using mathematics. And there are spin statistics theorems.
So you have to enforce extrapolations. I see.
There is no physics without condition. Right?
No, I know, but I don't know if anybody has actually looked at this problem. So that's the other thing. It's difficult.
In the statistics, there is good reason to believe we do.
I mean, the whole business of. I think I have to stop now.
One question there.
Me?
Yeah.
Yeah,
Shall I?
Yes.
So then I'm a little confused because when we use the equation of state, we get the mass, radius of the neutron star, etc. But we don't get this area. This ANS is the area, right? Area of the neutron star as a function of t, you were saying, time.
yeah. I mean that.
T
See,
going to infinity.
no,
That's
I
what.
mean, see, what you get are the boundary values. So to speak.
Yeah,
right?
but
So
T-
I'm talking about an approach to solve these equations. If I can
Then
take
time dependence, I don't understand.
No, you will not get the time dependence
Yeah,
in
that's
your way
what
of
I'm
doing it,
asking.
right? But here, I have these equations, right? Let's say these equations. So these equations involve the trapping horizon, which is evolving, right?
That
So
is from this end.
from that,
whole end.
yes. And now, I have to ask these questions, which I showed before. These questions. So basically, what you'll be computing is something like this at t equal to 0.
Zero.
Or what is the horizon at large time?
That's right.
So you're calculating, your work is solely with the boundary values, but the quantum gravity approach has to do with this. But I think that's a good point which Patrick is making. But however, you see, the moment I want to worry about the matter is very important here. Otherwise, I have a collapsed object. So I think the moment I deal with the matter, even using the entanglement entropy, the fermionic nature will be built in it. Okay? But somehow I should be able to avoid the intricacies of actually doing the dynamics. See, the thing about entropy is that you can get away with the counting. Can I do that? So that's the proposal.
Now, the point which we are asking is, what is the physical property which allows you to do this?
That's right.
That's not that's the question.
That's the question.
What prevents a collapse?
Yes. What prevents
Or
it?
prevent the collapse, and similarly the fermionic nature or the detailed nature of the neutron star doesn't come into the picture.
Doesn't play.
There ought to be some physical
Yes.
property which does this, if this picture is true.
That's right.
So, okay, with that, let's thank the speaker for
Thank you.
today.